So we're going to start chapter 3 today on the prime numbers. I realize we've accumulated quite a lot of exercises. Some of them we've looked at up to now. Some of them we've looked at in the tutorials. And my aim, remember, my aim was to put into these notes more than enough exercises. And so there's definitely more exercises there than we will ever get through within the tutorials. So, I make no apologies for putting in loads of stuff. I don't want people to be short of stuff to be working on. You should still aim to work through all these exercises, though, and mop up any we don't consider in class time yourselves outside. But when I'll be seeing you for the second number theory lecture this week on Friday, isn't it? So then I don't think I'll go through any new material then. I'll look back on all the exercises we've had up to now and do some examples and take questions from yourselves. So Nassim was asking about reading weeks and revision weeks there at the start. You consider this a kind of like a mini revision session or a bit of a pause, I guess, and looking back at everything we've come through and just going through more exercises, more of the proof type exercises, and just taking questions and clarifications from yourselves. Okay. So that'll be on Friday. So anything you want to prepare before then would be good. Come armed with questions that you want to ask me, things you want me to clear up or help you with, okay, for next Friday. Okay. So we find ourselves at the beginning of chapter 3 then. And chapter 3 begins with the definition of a prime number. Now, we've referred to primes plenty before now, and you will of course be aware of what a prime number is, but just for completeness sake, we give the definition. Okay, so a prime number, we talk about positive numbers, positive integers. So it's an integer strictly bigger than 1. So we don't include 1 as a prime number. And it's a prime number if it has no divisors except for itself and 1. Okay, back in chapter 2, when we introduced divisibility, we proved everything is divisible by 1 and everything is divisible by itself. So any integer strictly bigger than 1 has at least 2 divisors, itself and 1. If it doesn't have any others, we call it prime. Otherwise, we call it a composite or a non-prime. So, you're all aware the first few primes, 2, 3, 5, 7, 11, that's the start of the prime numbers, okay? And there are plenty of them, plenty of the prime numbers. And we're going to prove some basic facts about them today. Today we're going to prove the Fundamental Theorem of Arithmetic, which we discussed before. Fundamental Theorem of Arithmetic, theorem 3.3, says that every integer, every positive integer, factors into a product of primes. And moreover, the crucial part is this factorization is unique. Okay, you might write the product by reordering everything, but essentially it's unique. There's just one set of primes with multiplicities which divide the integer n, and n is a product of those primes, product of those prime powers. And there's no other way to express n as a product of a different set of primes. That's the Fundamental Theorem of Arithmetic. And before that, although it's not required for that, but we'll also prove, okay, I've said there are many prime numbers. We'll see shortly why there are an infinite number of prime numbers. So there's no end to the sequence of prime numbers. Okay. There's the first 5 of them there, 2, 3, 5, 7, 11. Just do a quick computer experiment using Sage. This line P, you can see here, P is defined as the list of every number little p, for p in the primes between 1 and 10,000. 1 and 10 to the 4. So P, this set P I've defined, holds all the prime numbers between 1 and 10,000. And it tells me there are 1,229 of them. So there's plenty of them between 1 and 10,000. Just talk a little bit, one of the outstanding conjectures about prime numbers, one of the results that we don't have a proof of one way or the other yet, is called the twin prime conjecture. in general, as you go out along the positive integers, the primes become rarer and rarer. They become less dense as you go out. So you find a lot of them early on in the integers, but you find less and less of them as you go through all the positive integers. Okay. Roughly, I mean, maybe intuitively feeling, because the higher a number it is, the more chance it has of being divisible by something less than. Okay. But there are an infinite number of prime numbers, so you never stop finding prime numbers. And curiously, it keeps happening. As you look out along the sequence of prime numbers, it keeps happening that you find so-called twin primes. Twin primes, a twin prime pair is a pair of prime numbers separated by 2. So it's a time when you get a prime number, and then 2 greater than that number is also a prime.
So like 3 and 5.
Like 3 and 5, 5 and 7, 9 and 11, 11 and 13. Okay, so there's lots of them early on. And they get less common. But by computer search, we have found many, many, many sets of twin primes. We could do a little Python program here to find all the twin primes in between 1 and 10,000. So this little loop says for every prime number p in this set, capital P have defined, if p plus 2 was also in P, then I append to the list of twins that pair P and P plus 2. So if we run that little program, it quickly scans through the 1200 primes there. So these are all the twin prime pairs. So, 1667, 1669. So these are all twin pairs of twin primes, all the ones that you can find between 1 and 10,000. So the last pair you encounter is 9,929, 9,931. Okay. Now there's a conjecture that there are an infinite number of these twin primes. We know the primes are infinite. We'll be proving that today. And it's a conjecture that there are also an infinite set of twin prime pairs like this. But that's still an outstanding question, which number theorists work on today. There has been some progress made on it recently. The way they're making progress on it is so this says there's an infinite number of pairs of primes separated by a distance of 2. But the way they work on it is to try and prove that there's an infinite number of pairs of primes separated by some much larger gap, and then gradually trying to bring that gap down. Now, it was only a few years ago that the first proof was made that there is a bound, that there are infinitely many pairs of prime numbers within some fixed distance of each other. And that original bound, it was like of the order of a few million or 70 million or something. But at least somebody finding that there was this fixed distance within which there are infinite numbers of pairs of primes, and that was amazing progress. And they've since been able to shrink that gap down a bit. Now, well, I'll come back to that result. There's an interesting story about it. I'll come back to that in a few lectures' time. We'll investigate it some more. There's a good article I have on it, which I'll post. So there are 205 twin prime pairs between 1 and 10,000. So even though we know lots of things about prime numbers, there are still very basic questions like this for which we have a conjecture. People suspect it's true, and we keep finding twin pairs as we search through ever greater and greater numbers, but nobody has a proof that there's an infinite number, and by the same token, nobody has a proof that there isn't. I think the general belief is that there should be an infinite number, but so that kind of points. That's one example of some of the unsettled questions around prime numbers. Okay. Let's make some progress. Let's actually prove some things. So the first thing we're going to prove, and we've kind of done it in passing before now, is this is the first part of the Fundamental Theorem of Arithmetic, proving that every integer factorizes into primes. Second part is that the factorization is essentially unique. So we can get the fact that everything factorizes into primes using induction. Now this is the alternative form of induction. It's what's known as strong induction, where you do induction without a base case. But it looks a bit funny because it looks like you're doing induction without proving an initial base case. Well, the initial base case is kind of incorporated into the main induction step. So this time, the assumption that we make is we assume the result, this result, that every integer factorizes into prime numbers, we assume it's true for every integer n between 2 and some point k. Now it's true. Actually, you can see the base case here, because if you take, I mean, it is true for 2, because 2 is a prime number, so 2 in particular factorizes into primes. 2 is just equal to itself. So, you know, you can see that the base case is kind of true here. But the induction assumption we make, we have to assume it's true for every number between 2 and some intermediate point k. Then what we're going to do is we're going to lengthen this, and we're going to prove that k factorizes into primes. So if everything strictly less than k factorizes, we're going to make the inductive link here prove that that assumption, the assumption that everything less than k factorizes, that implies that k has to factorize as well. And it's really just built on the definition of divisibility. It's just taking the definition of divisibility and just presenting it the right way. Okay. So here's how the proof goes. So we're taking this number k. We want to prove that k factorizes into primes. Well, by definition, k is either a prime number or it's not. Okay. If it is a prime number, then we don't have anything to prove. Okay. Because if k is prime itself, then it factorizes into a product of just one number itself. K is equal to the prime k. If it's not prime, so by definition it does factorize into something, or it has a divisor other than itself and 1. So if it's not prime, then it has a divisor k1. And so there exists another number k2, such that you can write k as k1 times k2. Maybe k2 might be the same as k1 if k is actually a square. But if k is not a prime number, then it factorizes as k1 times k2. And the important thing about k1 and k2 is they're both strictly less than k. So the assumption we've just made applies to k1 and k2. We assume that every number strictly less than k factorized as a product of primes. So here's two numbers, k1 and k2, strictly less than k. So k1 and k2 must factorize into primes by assumption. But then you're looking at a product of primes k1 multiplied by another product of primes k2. That's just a slightly longer product of primes. Get all the primes multiplying together to give k1, all the primes multiplying together to give k2. So you just multiply those two lists together, and you've got k expressed as a product of prime numbers. Okay. So assuming that everything less than k can be factorized into primes, that implies that k itself must be possible to factorize it into a product of primes. Okay. So we get that every number factorizes into a product of primes. Okay. So this proof is just kind of formally presenting the kind of intuitive process, you know, we presented a while ago, which was like, take a large number. Ask yourself, is it prime? Is 100 prime? No. It's divisible by something. It's divisible as 4 times 25. Are those numbers prime? No. 2 is 2 times 2. 25 is 5 times 5. Are these numbers that we found now all prime? Yes, they are. Just keep factorizing everything in sight. Eventually, you see that the number you started off with is a product of all these prime numbers that you reach at the bottom of this factorizing tree. Okay. Well, it's really that same principle, that same idea that's just presented here in the form of an induction. Okay. See, this first step, we decided 100 wasn't prime, so we factorized it into 4 times 25. Well, those are smaller numbers, and we're assuming you can factorize everything smaller into primes, which you do, then you just multiply together their prime factorizations, and you get the original. Okay. But the outstanding question, the remaining question is, you know, would I always get 2 by 2 by 5 by 5? Because I could draw the tree slightly differently. I could draw it as 2 times 50 to begin with. Of course, you do always get the same set of primes, but the thing is, we haven't really proved it yet. And supposing I started with, you know, some huge number, some, you know, ginormous number with billions of digits, you can appreciate that there'd be a huge number of different factorization trees I could present, different ways of breaking it down into prime numbers. How do I know that all those different ways of doing it will lead to the same collection of prime numbers at the end? Might it be possible we get 2 different sets of prime numbers? Okay, well, that's the question that's hanging in the air, which we're going to prove. We're going to prove the answer is no. You can never get 2 different factorizations. You always just get the same factorizations. Okay, but before that, we present what's probably the most famous result in number theory, which is that there are an infinite number of prime numbers. I'm going to write this out by hand, if only for just the pleasure it brings. It's like a particularly nice piece of music. You don't just look at it written down, you actually play it. You actually kind of step through it each time. So although you've got it written in the notes, you know, although you've got it written in the notes, if you're going to be a student of number theory, you should at least write this out a few times. Test yourself that you understand it by replaying it for yourself a number of times. Okay. So we're going to prove that there's an infinite number of prime numbers. So it's a proof by contradiction. Now, how do proofs by contradiction work? Proofs by contradiction work by straight away you assume that what you're trying to prove is false. You know, the first time you see it sounds a crazy way to go about proving it. Okay, but it's a very, very useful technique, a very, very neat technique. So we assume that what we're trying to prove is false. I.e., we assume there's a finite number of prime numbers. So we assume there's a finite number of prime numbers. So there's just some finite list of prime numbers. It could be many millions of them, or it could be just a couple of hundred. But we assume that there's just a finite number. Well, if there's a finite number, that means we can write them all down. So let's say they are P1, P2, P3, as far as the last one. Okay, so we number them, P1 up to Pn. Those are all the prime numbers we're assuming. So this is the lovely move in the proof. If you want to think of it musically, you think this is a lovely sequence of notes. If you want to think of it like football, this is a lovely dribble to get past the defender or something. Well, whatever your thing is, come up with some analogy. But this is where it happens. You consider the integer n. And it's a nice simple construction. You multiply together all the primes, and you add 1. Okay. Okay. It's nice and simple when you see it. But see, we assume there's a finite number of primes. Let's multiply them all together and add 1. But certainly an integer. Now, what have we just done? We've just proved, the previous proof, which we read from the notes, was that every integer factorizes into primes. So must this integer n. Okay. And m has at least one prime at least one prime factor. Okay, it must do. Maybe it's a prime itself, but if it's not a prime, you keep dividing it by factors, and eventually you reach an irreducible factor. You reach a prime number that divides it. So it's got at least one prime factor. Now we've just assumed there are only a finite number of primes, so the prime factor that it has must be one of these p's. Pi, say, where I is one of these index values between 1 and n. So at least one of these prime numbers must divide m. Okay. So Pi divides m. We also notice that we can take this equation and turn it around and write 1 as n minus p1 to pn. But now this is a way to express 1 as a linear combination of m and this product of prime numbers. It's n minus this product. But the point we're at now says that Pi divides m, and Pi certainly divides this product because it's one of the things along the way, isn't it? Pi is one of the factors here, and Pi also divides m. So by our theorem back in chapter 2 on divisibility, if you have some number, and here it's Pi, that divides m, it also divides the second part. Well, it's going to divide the difference. Okay? The difference is an example of a linear combination of the two numbers. So we're forced to the conclusion that Pi divides 1. So this is an example of the application of theorem 2.1, part 3. This was the fact that if you've got a number dividing two numbers, it divides any linear combination of them. Now we seem to have arrived at a prime number that divides 1, which kind of seems to imply that Pi is less than or equal to 1, because 1 is divisible by Pi. Now at this point, we start to say, well, that looks a bit strange, and it does, because by definition, prime numbers are strictly bigger than 1. So you can't have a prime number that's at the same time less than 1 and strictly bigger than 1. That's a contradiction. So this is a contradiction. By definition, prime numbers are strictly bigger than 1. And in the course of our argument here, we seem to have found a prime number that's less than or equal to 1. Okay. Now, for a short while, you get an awful fright, and you think, oh my, I've proved a contradiction. Which would, you had proved a contradiction that would make the 9 o'clock news. You'd be instantly world famous, and the whole universe would fall apart, of course, because logic would cease to mean anything. But we haven't proved a contradiction. What we've done is we've made a mistake somewhere in our argument. Now, the middle of the argument is fine. I explained it very carefully. I justified all the steps by reference to previous stuff. What is wrong in the argument is what we said at the very beginning. And what we said at the very beginning was, we said this: assume there's a finite number of prime numbers. Well, that's our problem there. Okay. We're not allowed to make that assumption because it leads to a contradiction. So we cannot make that assumption. It can't be, because then we have a contradiction. So it must be that this assumption itself is false. So therefore, there must be an infinite number of prime numbers.
Oh, so you get proving the assumption not true.
I prove that the assumption leads to a contradiction, and therefore it cannot be true, because contradictions can't happen. It contradicts something that we know to be true. By definition, prime numbers are bigger than 1. So you know it's true. So there are an infinite number of prime numbers. Just out of interest, just a brief show of hands. How many people had seen that before? How many people are aware of that proof before? Okay, great. So you should. I think this is a really nice. It's such a short proof. It fits on the one page. Well, almost. But it's I think it's readily. It's very nearly. It's quite approachable for non-mathematicians. You could fascinate your friends and family with this, I think. But it gets you to quite a powerful result. There are an infinite number of prime numbers. Now the primes are quite mysterious in ways, and there are lots of things we don't know about them. For instance, we don't know whether there's an infinite number of twin prime pairs or not. And we've no easy way to describe all the prime numbers. We're reduced to, in the search for prime numbers, we're reduced to just using the computer to exhaustively test each integer to see whether it's prime, by basically trying to divide it by stuff and seeing if you can ever divide it by anything less than it. We've no easy way to tell us what all the prime numbers are, but we do have a very quick way, in some senses, of proving that there's an infinite number of prime numbers. Okay. It comes out of the definition of divisibility and the definition of prime number itself. If you feel kind of awkward about thinking of it as a proof by contradiction, you can also think of it as a way of, instead of framing it as a proof by contradiction, you can frame it as a kind of a machine for producing prime numbers. So by investigation, we find a first few prime numbers, 2, 3, 5, and 7. So we find 4 prime numbers to begin with. Another way to think of this argument is it gives you a recipe to produce another prime number. However many primes you have, you multiply them together and add 1. Then by the proof we did at the head of the lecture, that number, all the primes you have multiplied together plus 1, this number is divisible by a prime. But this little argument here shows the prime that it's divisible by is not one of these ones. So therefore, there's another prime that wasn't on your list. Then you simply run the machine again. Now you've got a new list of primes that's at least 1 bigger than what you started with. Now you just do the thing again. You multiply them all together, you add 1, you get another integer. It has prime factors, but they can't be any of the ones you multiplied together, because otherwise it would have to divide 1. So there's a new prime number. So if you like, you can think of it as a machine which produces primes, and you can just keep turning the handle on the machine, because whatever output, a new prime you get, just simply feed it into the machine again, and it spits out another new prime. So that, in a way, proves that the sequence of primes is unending, okay? Because you just keep running this argument to produce a new prime. That's a kind of another way to frame it, which isn't framing it as a proof by contradiction. Any questions about it? Or about that argument, or any clarification you'd like on it? Okay, so we got an infinite number of prime numbers, which is good. Yes?
What does that thing mean, m equals, like it's p times p1 times p2?
Those numbers multiply together. P1 multiplied by P2.
Oh, so all the prime numbers multiply plus 1?
Yeah.
Oh, right, okay.
Yeah. Okay. So let's go back to our notes. Now we want to get to our FTA, our Fundamental Theorem of Arithmetic. Okay, so as I've said, we've already proved the existence part, that every integer factorizes into prime numbers. Here's another example, 495, 3 squared by 5 by 11. Now, okay, we can write down a slightly different looking prime factorization by just reordering the prime numbers. But really, you know, this we regard as the same as that. All we've done is change the position of the 3, whatever it is. So, apart from reordering them, apart from reordering the prime factors, what the theorem says is that that the prime factorization is unique. You can't factorize 495 or any other integer. You can't factorize it differently into primes. Okay? Now, the way the theorem is stated, it also sets up. So just to understand this, what's going on in this notation here, it says every positive integer factorizes into product of primes n. So the P1 up to PR, those are the different prime numbers that divide n. And they all have indices, alpha 1, alpha 2, etc., up to alpha r. So the alpha I are positive integers, and that just records the power that the multiplicity of that prime is a factor of n. So in the 495 example, the 5 and 11 have a power 1, so alpha is equal to 1 for the 5 and 11, but for the 3, it's alpha equals 2, because 3 is a multiplicity 2. Factor twice of 495. Okay. Now, so what we're setting out now is to prove the uniqueness part of this. Okay, and we got a lemma beforehand. It's called Euclid's lemma. Now, this was actually a previous exercise. So I may have done it in your tutorial or not. There's 2 tutorial groups. I can't remember if I did it in both. But it's one of the previous exercises to chapter 2. It's labeled as such there. But we repeat it here because it's a very important result. It was quoted in terms of greatest common divisors there, but here we phrase it in terms of prime numbers. So what it's about is, if you've got any 2 integers a and b, if you've got a prime number that divides the product, then it must divide either a or b. It might divide them both, but it must divide at least a or b. Okay. I mean, just to see some examples, 2 divides 100 as we saw, so 2 divides 4 by 25. But you can see that that's true, yeah, because 2 divides the 4. In the same way, 5 divides 4 by 25. Yeah, we know that because 5 divides the 25, so of course it's going to divide 4 times 25. Whenever you see a prime dividing a product of 2 numbers, it must divide at least one of the numbers. It might divide them both, but it must divide at least one. Of course, it's not necessarily true for composite numbers, because 50 divides 4 by 25. 50 divides 100, but 50 does not divide 4, and nor does it divide 25. Okay? So composite numbers don't have this property. But prime numbers, it's possible to find composites dividing products where the composite does not divide either of the factors. But for prime numbers, it's impossible to find. Now, one way of thinking of this is being, yeah, if a prime divides a times b, it has to divide one of them because we can factorize a into primes and we can factorize b into primes. But you can't factorize p because p is a prime number, so you can't split it apart and put part of p in a and part of p in b. Because that's what you can do with the composite number. You see, the 2 from 50 goes into the 4, and the 25 from 50 goes into the 25. So you take the 50 and you split part of it into this factor and part of it into that factor. That's how you get that 50 divides the product, but not either of the factors. But of course, you can't do that with the prime number because you can't split it apart. Now, the only problem with that argument is it relies on knowing that A factorizes it into primes and knowing that B factorizes into primes. And we don't really have that yet because we haven't proved the uniqueness of the fundamental theorem of arithmetic. So what we'd like to give here is a proof of this result that doesn't rely on prime factorizations. It's only going to rely on the greatest common divisor, ideally. So here's the proof. This is really nice as well. It uses, so the ingredients of it are, we're going to use the idea of the greatest common divisor and the fact that the greatest common divisor of two numbers is 1. That's equivalent to there existing a linear combination of the two numbers equal to 1. So that was that played a large role in our tutorial exercises last week. So we suppose the prime number p divides a times b. Now we're aiming to show that p must divide a or it must divide b. If p happens to divide a, then we're done. So then we can just go home. We're finished. But if it doesn't divide a, then we've got something to prove. If p does not divide a, it must be that p divides b. If we can prove that, that will prove the lemma. Okay. So now we're in a situation where we've got p dividing a product a times b, but p does not divide a by assumption. Now we're going to prove that it must be the case that p divides b. But you see, being at this stage with the assumption now that p does not divide a, then we can bring in the greatest common divisor. Okay? Because p is a prime number, so it only has two positive divisors, one in itself. So there's only two possibilities for the GCD of a and p. The GCD of a and p, it has to divide both a and p. There's only two things that divide p, 1 and p. We've already ruled out one of them as being a divisor of a. So it must be that the greatest common divisor is this one, 1. Okay. 1 divides everything. The only other thing that divides p is p itself. But we've assumed now that p does not divide a. So now we know that the greatest common divisor of a and p is 1. And from what we know already by Euclidean algorithm, if you like, if the GCD of a and p is 1, that means you can write 1 as a linear combination of a and p. So there exists a pair of integers n and m, and when you form this linear combination np plus ma, you get 1. Now we want to prove that b is divisible by p. Now b doesn't feature here in this equation yet, but there's an easy way to make b appear in this equation. Just multiply both sides by b. When you multiply on the left by b, you suddenly have b on its own, which is good. And we have nbp and mab on the right-hand side. But then you just look at the two numbers here, and you see the first one is divisible by p. It's got a p in it. And so is the second one, because the second one is a multiple of a times b. But one of the conditions in the theorem is that the prime number p divides a times b. So now we know p divides both parts of this sum, so it must divide. It must divide the sum itself, and the sum is equal to b. So we've reached the conclusion that p divides b. Okay. So if a prime number p divides a product, it must divide either of the. It must divide at least one of the factors, a or b. The way the proof works, because if it didn't divide the first factor, we proved it had to divide the second factor. So that proves it must divide at least one of the factors. Okay. Is that okay? Any questions on that? That's Euclid's lemma, and that's an important stepping stone towards the proof of the FTA itself. Now you can easily generalize this lemma to more than two factors. So we stated it there as if p divides the product of two things, it must divide one of them. Well, you just rerun the argument. You can easily generalize it to any number of factors. So So we know if P divides a product of any amount of factors, A1 up to AN, it must divide at least one of them. Okay? The reason for P dividing this product is because it divides at least one of them. And now we can give the proof of the FTA. It's again a proof by strong induction. So we're proving now the uniqueness part of the FTA. We're proving now that whatever way you factorize a number into a product of primes, that's the only way of doing it. You can't reach a different set of primes. If we do it by strong induction, we assume the result is true. I've slightly mixed up my n's and k's here. I'm using them in slightly different ways how we normally use them in proof by induction, but still correct. We're assuming that it's true for every integer strictly less than n. Normally we have k as the objective thing here, but now it's n. Sorry. We assume it's true for everything strictly less than n. So we're assuming everything strictly less than n factorizes uniquely into primes. So now we want to prove that n factorizes uniquely. So we assume it's true for everything less than n. Now within this, how we're going to prove that inductive step is a little proof by contradiction, if you like. So we suppose we've got two prime factorizations of n. So we suppose that it's possible to write n as a product P1 up to PR of prime numbers, and also as a product Q1 up to QS of prime numbers. So each of the P's are primes, each of the Q's are primes. We're potentially looking at two different factorizations there. There's R numbers in this list, in this product, and there's S numbers in that. They're potentially different. But we just hit it straight away with the lemma. Okay? We can tell from looking at this equation, 3.11, that P1 divides n. Okay, here's P1 as one of the factors of n. So P1 divides n. So straight away we know P1 divides the product of all the Q's. We just apply the lemma to that. This prime number P1, it divides the product of all the Q's, therefore it must divide at least one of the Q's. That's what the lemma we proved just said. Now, we can just suppose that the Q that it divides is Q1. For this in Q1, we'll just relabel all the Q's to make the Q that it divides Q1. So whichever prime number P1 divides, we just bring that to the front of the list of Q's. So we'll just assume that P1 divides Q1. Divides one of the Q's. But Q1 is a prime number. By definition, it's a prime number. We said that at the start. So if it doesn't have any factors apart from one in itself, so it must be the case that P1 and Q1 are actually the same number. P1 equals Q1. So we proved that one of these primes is equal to one of those primes. Well, then we can divide n by P1. It's the same as dividing it by Q1. P1 is the same as Q1. So now we've got a smaller number, n prime. It's smaller because we've divided it by something larger than 1. And this smaller number is potentially written as a product of primes in two different ways. But now the induction hypothesis is used, because we assume that the result was true for everything strictly less than n. So here's an n prime strictly less than n. So it must be that its prime factorization is unique. So we're not looking at two different lists here. We're looking at the same list. Maybe reordered, but essentially the same list. So in particular, R is equal to S. The same number of things here. And each of the P's is equal to one of the Q's. At worst, it's just a relabeling of the same set of prime numbers. We reached that conclusion by applying the induction hypothesis, because we assumed the prime factorizations were unique for everything strictly less than n. So that tells us that these two primes are the same set of primes. And the prime we took away originally from n was P1, which we knew was the same as Q1. So P2 up to PR is the same as Q2 up to QS as lists of primes. it means the two original lists must be the same as well. Okay. So that proves that n factorizes uniquely into primes. And the thing we used for the proof was the induction hypothesis that everything less than n factorized into primes. Again, you see the induction happening. If everything less than some number factorizes uniquely into primes, so must that number. So you just keep inducting through all the integers, and we get that the result is true for every integer. So that's good. That was good work today. We saw proof for the infinite number of primes and the proof that everything factorizes uniquely into primes. So do look over those, do study those, get to know those proofs. And on Friday, we'll do some intensive work with any of the exercises we've accumulated up to now. Okay? So I'll see you then.